Hey, ChemStars, this is Mrs. Vanderwall bringing you another section of ChemStar video. We are in Chapter 6 again. We are in Section 6.2 called Covalent Bonding and Molecular Compounds. If you haven't done so already, can you please get out your periodic table? You're really going to need that to look at. So we'll go ahead and do that now. All right, welcome back. Hopefully you have your periodic table with you. We're talking about molecules and molecular compounds. This whole section, chapter 6, is talking about really covalent molecules. We're talking about your non-metal bonds, if you will, these molecules held together by non-metal sharing electrons, okay? So that's again what a covalent bond is. There's our atoms held together by what? By sharing the electrons. The molecules, a neutral group of atoms joined together by covalent bonds, okay? There are two kinds of things we need to look at, and the first one is right here, diatomic molecules. These are the elements that can exist only in their elemental state if they're paired with their other atom. They're like, their twin, if you will. So these are your 7 diatomic molecules. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine can only exist as H2 or O2 or F2 as an element. Of course, they can be in other compounds, if you will, but I'm talking about just their elemental form would be a diatomic molecule. They are held together by covalent bonds. They are sharing electrons, okay, but they consist of the same atoms. A molecular compound will consist of 2 or more atoms of different elements. So we're just making that quick distinction there, okay? So let's see what we're doing down below. So a molecular formula shows how many atoms of each element a molecule contains. So the very front page of these notes, we compared ionic versus covalent. So an ionic formula, I wouldn't necessarily call this a molecular, all right, but an ionic formula shows the ratio of elements, all right? So let's go back. So ionic was your metal, non-metal. So sodium chloride, we use that all the time as our example. And here I brought back like a picture of sodium chloride. Notice that you have a 1-to-1 ratio. For every purple sphere, there's a green sphere. So that would be an ionic compound. The ratio is 1-to-1. I don't have one purple and one green. I have a lot of them. I don't know how many there are, but their ratio is 1-to-1. I also found one from calcium chloride. Now, how will that work? So here is a picture of it. So look really closely. This green is your calcium, and it's bonded to 2 chlorines, if you will. All right, so when I say bonded, I mean like the chlorine accepted the electrons from the calcium. But the ratio, I don't know if you can see them really well, but there are probably what looks like 12 probably chlorines, the small ones, for every well, I have 6 green calcium. So I have 2 here, I have 2 over here, I'll probably have 2 over here, 2 here, 2 down here, they probably can't see them, and 2 over here. So there are 2 chlorines for every 1 calcium, but they're still put together in an ionic formula. So I don't have just 1 calcium and 2 chlorines in my crystal. I have the ratio is 1-to-2. Now, a molecular, again, we used water before as an example, as a molecular compound, and it really does have only 2 hydrogens to 1 oxygen. That's it. It's not a ratio. Well, I guess it is, but it's exactly 2 hydrogens to 1 oxygen. Then I thought I was going to get wild and crazy, and here's table sugar. All right, and if I look closely, I really do have 12 larger gray spheres and 22 small. These are my small hydrogens, and I have 12 red oxygens. So that is 1 large molecule of sucrose. Okay, so again, a molecule has an exact number of atoms in there, and ionic has a ratio. Okay, so let's review Lewis dots. All right, well, how do I review Lewis dots? Well, I need to know valence electrons. So let me scroll down here. All right, I know we've looked at this before, Okay, we're talking about valence electrons. And what is it I want you to think of? I want you to look at your periodic table. Okay, so I'm going to go scroll to a periodic table. Hang on. And here's my periodic table. Hang on. I made my periodic table a little bit wider so the whole thing fit in. And how do I figure out valence electrons? Do you remember how I did this? I started off with 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Remember this? Then I hit boron and it's 3, 4, 5, 6, 7, 8. Do you remember doing that? So these are my valence electrons. If you don't already have it written on top of your periodic table, you might want to do that. 1, 2, 2, 2, 2, 2, 2, 2, right? When you hit boron, 3, 4, 5, 6, 7, 8. What does that valence electrons mean? Outermost electrons. Why did we care about those? Because I warned you, those are going to be our bonding electrons. I care about the outermost because I'm going to bond with those, okay? And now we're going to really need to know how to do this, okay? So hopefully this reminds you of how to do valence. Oh, by the way, helium only has 2, right? So I can go back to where we were in our note. All right, so hopefully you're looking at your periodic table. How many valence electrons did lithium have? Well, here's lithium. It has 1. All right, so here's my 1. So how do I do Lewis dots? Well, I just put 1 dot on lithium. Here you go. Boop. There it is. All right. So find beryllium. How many valence electrons does beryllium have? 2. Remember doing that? So I'm going to do this. 1, 2. Do you remember this? So boron. How many does boron have? I bet you can just guess. It has 3, right? 1, 2, 3. Well, look up carbon. How many valence electrons does carbon have? Well, hope you're looking. It is 4. So I'm going to do this. 1, 2, 3, 4. Nitrogen. Well, what's a little bit different about nitrogen? It has 5, so it's 1, 2, 3, 4, 5. Do you remember doing this? Oxygen has 6. 1, 2, 3, 4, 5, 6. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. And the neon has 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, hopefully you remember doing that. Now, the octet rule of bonding and covalent binding, what's an octet? Well, it's 8. So octet means 8. Ionic compounds will achieve the octet rule by gaining or losing electrons. In covalent electron or covalent molecules, the electrons are shared, okay? And so that the atoms will attain the electron configuration of noble gases. What does that mean? Well, how many electrons does my noble gas have? 8. So they're going to share. So there's 8 electrons around it. Let me scroll down. All right, now hydrogen gas is going to be an exception. Hydrogen will have what's called a duet of electrons. So if you're thinking of a singing group and there's a duet, how many singers are there? There's only 2. So hydrogen is an exception. You only want 2 electrons around each hydrogen here, not 8. So how do we do this? Well, let's look at hydrogen again real quick on my periodic table. Here's hydrogen. How many valence electrons does each hydrogen have? Hydrogen has only 1. So here is my diatomic molecule. All right, so it's my Hofbrinkel, H2. And so this hydrogen, oh, let's do it this way. This hydrogen, let's call it my red hydrogen. Let's make this my red one, has 1 valence electron. And how about this hydrogen? Let's make this my blue hydrogen. How many valence electrons does this one have? It has 1. And I'm going to put it right there. So look at that. They are sharing their electrons. Okay, so how many electrons does my blue hydrogen now claim? 2. How many electrons does my red hydrogen now claim? 2. How did they each get that? By sharing their electrons, all right? So why does hydrogen only want 2? Well, what's its closest noble gas? I think it's helium. Well, helium only has 2 electrons. What does that truly mean? That hydrogen will have a filled 1s shell. All right, and what did we say about filled shells? It's highly stable. All right, so hydrogen is going to share its electrons, so it's going to have a filled shell in a sense. all right, and that is highly stable. So look at the noble gas, all right, see how many electrons, or excuse me, see how many valence electrons it has, all right, and that's what each other element we're going to have. So in this case, hydrogen is going to be like helium. Helium has 2 electrons. It has a filled shell with 2 electrons, so that's what hydrogen is going to do. All right, let's go on to the next page. We're going to see what other elements do. So all others will want a full octet. Octet meaning 8, achieved by what? By sharing, okay? So how many valence electrons does hydrogen have? Well, let me think. Hydrogen has only 1 electron, correct? So I'm going to do this. And let's look at chlorine next, okay? Well, how many valence electrons does chlorine have? It has 7, okay? So with 7 valence electrons, let's make this one blue. So here's chlorine in my blue. All right, here's Cl. It has 7. Watch. 1, 2, 3, 4, 5, 6. I'm going to skip this. There's already 2 electrons. 7. So there are 7 blue electrons and 1 red electron. And what does this do for me? Well, hydrogen now can claim its 2 electrons, so it has a filled 1s shell. And then chlorine over here, okay, has now claimed 8 electrons. It's sharing these electrons. The overlap is the sharing. So chlorine has 8 electrons around it, and it has a filled shell, okay? So it says, why does chlorine want 8 electrons? It's a filled shell. Chlorine will now have a filled, actually it's a 3s. Let me fix this quick. A 3s, sorry about that, and a 3p shell, okay? And that means it's going to have that stability like its noble gas, okay, like argon. All right, so a single covalent bond are 2 atoms held together by sharing a pair. How many is a pair? That's 2 electrons. See this right here? I'm sharing 2 electrons. So H2 above is a single covalent bond. That means on the prior page. And so this HCl is a single covalent bond because it also has 2 electrons. So an electron dot diagram, such as the one on the prior page, such as this, represents the shared pair of electrons of the covalent. You can also do this by using dashes, all right? So where you see a dash represents, what does it say right here, everyone? 2 electrons. So a dash is 2 electrons, okay? So right here, how to draw Lewis dot diagrams and structural formulas, all right? So here are the rules, okay? Very important. So the first atom in the formula is called a central atom. It's in the center. Except for hydrogen, it can never be central. Well, why? Because it's only going to have 1 bond. Or if it's in the center, you're going to have more than 1 bond. So then what? Place the correct number of valence electrons around the central atom. There'll be single electrons around the central atom, otherwise there'll be a noble gas. Place the non-central atoms at locations of those single electrons. Place the correct number of valence electrons of the non-central atom around this. Remember, there can be 2 and only 2 electrons in a bond. So each atom should now have 8 electrons around, except for hydrogen, which will only have 2. To check your work, this is important, count up all your valence electrons and verify they add up to the number of electrons of each individual atom. So let's kind of be flipping back and forth for these rules, okay? So let's try this. Okay, so for example, F2. Well, how many valence electrons do I have? Each fluorine has 7 electrons, right? For a total number of 14. So how do I do this? Well, each fluorine has 7 electrons, right? I'm going to start here. 1, 2, 3, 4, 5, 6, 7. All right, why did I skip that? Because what's going to happen? I'm going to do the same thing. 1, 2, 3, 4, 5, 6. I'm going to skip this 7. Okay. So let's kind of go back and see what I just did. What did I do? Okay. So I really didn't have a central atom. I had F2. Okay. I placed the correct number of valence electrons around each fluorine. there will be single electrons around the central atom. Okay, I did have one. That was the one on the left, or on the right to start with. Place the non-central atoms at the locations of the single ones. Place the correct number of valence electrons of the non-central atom around this. So I put the number of electrons around each fluorine, really. And there can be two and only two electrons between the two. It says to check your work, count your valence. All right, let's see here. How many electrons? Well, let's check this out. How many total electrons does this fluorine claim? Ready? 2, 4, 6, 8. How many does this fluorine claim? 2, 4, 6, 8. So each fluorine has 8 electrons around it. And now let's count our total number of electrons. Ready? 2, 4, 6, 8, 10, 12, 14. Isn't that what that is? So then how do I do the structural diagram? I put the bond between them, and now I just finish off with all the dots, all right? Remember that dash represents 2 electrons, right? So 2, 4, 6, 8 around the left-hand fluorine, 2, 4, 6, 8 around the right-hand fluorine. I have a total of 2, 4, 6, 8, 10, 12, 14 electrons. So let's look at water. I have 2 hydrogens and 1 oxygen. So I have 2 hydrogens with 1 valence each, plus oxygen with 6. Well, 2 plus 6 is 8. So oxygen is my central atom. How do I know that? Well, it can't be hydrogen, so it must be oxygen. So I put oxygen here. Now, how many valence electrons does each oxygen have? 6. Ready? 1, 2, 3, 4, 5, 6. It's a little different pattern as before. Normally I would have gone like 1, 2, 3, 4, 5, 6, but I already have my hydrogens there, so I'm going to put a singleton electron where my non-central atom is, all right? So now each hydrogen comes in with 1, oops, try that again. Whoops, something happened here. 1 here and 1 here, okay? So what have I just done? Each hydrogen claims 2 electrons. That's good news for hydrogen. And what does oxygen do? Oxygen claims these 8. How many total electrons do I have? 2, 4, 6, 8. That works. All right, and then I'm going to do this. I'm going to put a bond here and a bond here. All right, and then I have 2 lone pairs, one on the top and one on the bottom. So I only need, I hope you're listening, 2 electrons around hydrogen. Here it is, and here it is. Oxygen still has 8 electrons around, 2, 4, 6, 8, and that's how many I should have. So let's look at nitrogen next. All right, nitrogen has a valence of 5. There are 3 hydrogens with a valence of 1. So 3 times 1 is 3, so 5 plus 3 is 8. I have 8 again. All right, so what am I going to do first? I'm going to put my nitrogen in the middle. And now I'm going to put its 5 valence electrons around. Okay, so where there is a singleton electron, I'm going to put my H's there. I have an H here. I'm writing too big here. I have an H here with its singleton electron, and I have an H here with its singleton electron. Okay, so what have I done? I have 2 around hydrogen, 2 around hydrogen, and 2 around hydrogen. Isn't that what I want it to be? Sure is. Whoa! Sorry about that. And then I have 8. There's one right here. I kind of drew over it. I have 8 around nitrogen, which is what nitrogen wants. And I have a total of 2, 4, 6, 8 electrons. That's perfect, all right? So how do I do my structural? All right, I'm going to put a dash and a dash and a dash. What do those dashes represent? 2 electrons. So here is this, and here is this. Now, how many electrons does nitrogen have right now? 2, 4, 6. It needs 2 more, and there they are. That's this lone pair here. So let's check out. Okay, so here's CH4. I have carbon with a valence of 4. And I have 4 hydrogens. See that little subscript? 4 hydrogens with each hydrogen with 1. So 4 plus 4 is 8. So let's try this one. So here, let's do carbon first. All right, and carbon has 4 valence electrons, right? And now I need hydrogen, and each hydrogen comes in with 1. You can be doing this too. All right, each hydrogen comes in with 1. And there we go. So this hydrogen has 2 claimed. This hydrogen has 2. This hydrogen has 2. And this hydrogen has 2. All right. Each hydrogen has exactly what it wants. And notice here's carbon with its 8. Isn't that great? All right. So now how do I do this? Here's carbon. Put dashes, and then here's your H's, right? Dash H. Dash H, dash H, right? And it's the same thing. So actually, does a carbon have any lone pairs on it? Not at all. So that works perfectly. 2, 4, 6, 8 around carbon. Why don't you pause this and you do sulfur dibromide? So sulfur has 6, bromine has 7, but I have 2 bromines for a total of 20. So I'm going to do my sulfur with its 6. All right, and now bromine has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. What is that? What have I done? Bromine has 8. Bromine has 8. And sulfur has 8. And here it is. So that works out great. Oh, by the way, I should count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It works. If you don't believe me, count yourself. So again, how does this work? I have these guys here. Put 8 around, or 6 more around bromine for a total of 8. Put 6 more around bromine for a total of 8. And I'm going to have 2 on sulfur and 2 more on sulfur. So this lone pair is that lone pair. This lone pair is that lone pair. So there you go. Go ahead and do chlorine gas, Cl2. All right, so pause this and go ahead and do chlorine. Okay, welcome back. I hope you did it. All right, so there are 2 times 7 is 14, so I should have 14 electrons. So let's do this. Here's chlorine. I'm going to put 7 around chlorine. 2, 3, 4, 5, 6, 7. I can put 7 around this chlorine. Ready? 1, 2, 3, 4, 5, 6, 7. Well, look at that. So there are 8 around this chlorine, and there are 8 around this chlorine, and that works out perfectly. Let's count. 2, 4, 6, 8, 10, 12, 14. That's perfect. So to do this, put your bond, and now make sure there's 8 around each chlorine. Okay. Oops. There you go. The next one is actually hydrogen peroxide, all right? Make each oxygen a central atom and see how you do. Go ahead and pause this and do H2O2. Okay, welcome back. So here I have 2 hydrogens with 1 valence electrons and 2 oxygens with 6. When I add this up, I get 14. All right, so this gets 6. Remember how we did that? 1, 2, 3, 4, 5, 6. So I put my single electrons where my other atoms are going to be. 1, 2, 3, 4, 5, 6. And then I'm going to put 1 valence electron with hydrogen, and there I go. So look at this. This hydrogen has 2, and this hydrogen has 2. And then this oxygen has 8, and this oxygen has 8. They have 8 by sharing, don't they? So how do I do this? I put the singleton, those are my bonds, and then I go drink, drink, oops, there, and then 2 more here, 2 more here, and 2 more here. So remember, these are my lone pairs. They have no bonds on them. Each oxygen has 2 lone pairs. So there you go. We got 1 more to go. Can you do this last one? So please pause this, and when you're done, come back. All right, welcome back. So phosphorus has 5, chlorine has 3, there's 3 chlorine, sorry, and each chlorine has 7. When I add 5 plus 21 makes 26. So here's my phosphorus, and it has 5 valence electrons. Again, I do that so that I put my singleton electrons where my bonds are going to be. All right, and then chlorine has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Well, guess what? Each chlorine has 8 electrons around it now, doesn't it? Yay, filled octet. All right. And what do you notice about phosphorus? Phosphorus also has 8 electrons around it if you did it right, and it works out perfectly. So all's left is to do this. Make sure you put the lone pair on the phosphorus. That's this lone pair right here. And I'll put all these extra ones around the chlorines, all right? Remember, each element except for hydrogen will need 8 around it. So that's what I'm doing right now, putting the 8 around it. Okay, and I believe that's the end of this session. So we'll be practicing this in class, don't you worry. But in the meantime, don't wait to be great. We'll see you next time. Bye-bye.